Hi, I'm Kacper. I'm a solution engineer here at Monolith. Today, I'll walk you through an anomaly detection demo using battery module cycling data. This dataset comes from dynamic drive profiles, which are often tested in labs for battery manufacturers. These profiles are provided by OEMs, and because they vary daily, it can be difficult to spot when something goes wrong. In this specific dataset, we have 12 individual cell voltages. We've got an overall module current and a module temperature. We're keeping it simple, but in reality, many more channels are usually recorded. The value of anomaly detection is catching issues early. When integrated into the workflow, it can highlight anomalies before they escalate, enabling engineers to stop tests sooner, free up expensive cyclers, and focus on collecting useful data. We typically train models on early cycles that have been reviewed and are known to be reliable. Here, I'll use cycles 1 to 3. Looking at all the cell voltages in cycle 1, we can see that they are behaving relatively the same throughout the whole cycle. Moving on to the module temperature, we can see that it's fluctuating around a stable 25 degrees throughout the whole cycle. And finally, the module current is behaving respective to all the cell voltages and the module temperature. We can then look through cycles 2 and cycle 3 and see the same behavior across those two. We then want to use this data to train our anomaly detection model. The process is pretty straightforward. Let me open up our anomaly detection model step here. We firstly pick our nominal data, which in this case will be cycles 1, 2, and 3. We'll select our time column, as the data that we're dealing with is time series. Our model is an autoencoder, and it will learn the data as a series. And we'll also pick the channels we want to evaluate. And in this case, it will be all the parameters that we're capturing in our dataset. We also want to set our hyperparameters. These can be changed and refined as more data becomes available. Once we've trained the model, we can apply this to later on cycles. So firstly, we can apply it to cycle 4. We visualize our results in a heat map. In this case, we have quite low anomaly scores in the file across the different channels. We can also visualize our data in a time series plot here. So we'll see our actual data in the blue line. We can see our predicted data in the green line, which is a reconstruction of our autoencoder. And then this will assign an anomaly score based on the different hyperparameters that we've set in our model training. In this case, the anomaly scores are quite low, therefore there aren't any anomalies. We can also set a threshold of what anomaly score we consider to be anomalous. So in this case, if I put in a threshold of 0.8, we can see that my heat map is nice and low anomaly score all throughout. I can then apply my anomaly detection model to cycle 5. Reviewing it with a manual eye, there's nothing that is standing out to me in the cell voltages. However, once I apply our model to cycle 5, we can see a high anomaly score in cell number 9. We can further inspect in our time series plot. In this case, maybe when we look at the actual data and predicted data, we don't see anything at first glance, but we get a high anomaly score in this area of the cycle. This may indicate that the cell voltage is slightly deviating from normal and might indicate that we should stop the test early. We can also isolate this channel by putting that anomaly score threshold and see that is the only elevated anomaly score throughout our whole cycle. In this case, we can flick through the data and look at cycle 10. In cycle 10, the actual cell voltage in cell 9 has deviated a lot from the rest of the data. But because we were able to flag it in cycle 5, the engineers could act earlier, prevent failures, and reduce unplanned downtime. In itself, extend the whole system life, ultimately helping to build better batteries.